Good afternoon, ladies and gentlemen. Welcome to the showcase hosted by Qualcomm. I'm Igor Kharlashkin, Director for Business Development of Qualcomm Europe, with my prime focus for the business development in Russia and Eastern Europe, CIS. It's my pleasure to moderate the session Status and Experience of 5G millimeter wave deployment. I'm sure you hear a lot from Qualcomm on millimeter wave, like 5G becomes real only with the millimeter wave. Today, with the help of 4 experts from the 4 companies, we will go exploring on multiple topics. Next slide, please. So where millimeter wave enables significant monetization potential, how millimeter wave provide new market capture for operators while being more cost efficient and highly attractive business viability. Following the panel session on rural connectivity, I think our showcase will make a lot of sense to you. So with this, I would like to introduce the first speaker. Jeanette Stewart is a partner in Ellison Mason, a leading telecom consulting and research firm. Jeanette works extensively on the spectrum policy and spectrum valuation, and the millimeter wave has been a recent area of her focus. So welcome, Jeanette, and the floor is yours, please.
Thank you very much, Igor. Good day, everybody. I'm going to be presenting the results of a study that Analysys Mason has conducted this year together with Qualcomm. Next slide, please. So the study was published in June this year. The study commenced at the start of this year. It covered the status, the costs and benefits of 5G millimeter wave deployment in Europe, conducted on behalf of Qualcomm together with Ericsson. The scope of the study was the European Union 27 markets, along with Norway, Switzerland, and the UK. However, we believe the results of the study are comparable across the whole of Europe, including Eastern Europe and Russia. Inputs to the study included our own research, secondary research of published announcements, our own economic modelling, and some primary research, which was a series of interviews with mobile network operators in different markets, both within Europe and beyond. Next slide, please. A summary of our key conclusions are as follows. We found that millimeter wave was generally understood to complement mid-band 3.5 gigahertz spectrum for a range of 5G use cases in Europe in different environments, both outdoor coverage and indoors. And that supports a conclusion that regulators should assign this spectrum specifically in the 26 gigahertz band, which is the band harmonized in Europe, if not already done. Our economic modelling suggests significant economic benefit, and the primary research suggested that MNOs were collectively expecting to use millimeter wave to address a variety of use cases, which I will come on to in a subsequent slide. Next slide, please. So we found that 26 gigahertz deployment enables several expanded use cases as well as new use cases. So by expanded, I mean that 26 gigahertz millimeter wave might be deployed primarily together with 3.5 gigahertz spectrum or other spectrum in a 5G network. It might also be deployed, though, as dedicated cells. So we found that millimeter wave would support a variety of mobile broadband use cases, and this is specifically focused on deployment in dense locations where capacity is required. So applications such as gaming, AR, VR, tourism, retail, industrial use cases. We found several markets will find use for 5G fixed wireless access using 26 gigahertz, and that can provide high-speed wireless broadband to homes and offices. And there's also a range of uses at specific locations where connectivity needs can be addressed perhaps more flexibly with 26 gigahertz, including the potential for optimization of uplink and downlink capacity. Next slide, please. Just as input to the study, we noted that 26 gigahertz licensing has been slower in Europe than for other 5G bands, primarily 700 megahertz and 3.5 gigahertz, but is now accelerating. As shown on the slide is the situation as per June this year when we conducted the study. Next slide, please. Onto the economic modelling. We modelled a mixture of millimeter wave architectures in our economic modelling. The economic modelling was focused on looking at costs of deploying millimeter wave compared to the GDP uplift benefits. So we calculated costs and benefits on top of a base case of 5G mobile broadband deployments. We looked at a mixture of use cases, different environments, urban and suburban, outdoor, fixed wireless access, industrial, etc. We modelled also a mixture of architectures, both macro and micro, some macro sites using 3.5 gigahertz upgraded with 26, but also dedicated 26 gigahertz cells as well. Moving on to the next slide, please. So shown on this slide here is the results of our economic modelling, aggregating across all use cases for the 30 markets. We can show on the slide here that the total GDP uplift is 140 billion euros by 2040, so that's cumulative, and that is against around 21 billion of additional deployment cost. And just shown on the slide here is how the benefits and costs are split across the different use cases that we modelled. Next slide, please. One of the interesting parts of the study was to inform our economic modelling. We interviewed several mobile network operators who at the beginning of this year were starting to deploy millimeter wave spectrum or were considering how to deploy and were conducting trials. And what we found from those interviews were that stakeholders had identified several potential environments where millimeter wave would be particularly helpful to deploy. This includes multiple outdoor and indoor locations, typically using 3.5 gigahertz or lower bands for wide area coverage, but having the millimeter wave available in dense areas or in other specific locations where connectivity is needed. So a variety of uses, including mobile broadband type applications, 5G based fixed wireless access, smart factory, street hub kiosks, so that's where you would be in a city centre, for example, and receive a very high downlink capacity, for example, and then venue-specific coverage, tourism, sports, stadiums, other events, etc. Next slide, please. Stakeholders particularly noted the capability of millimeter wave for high capacity and also the flexibility to vary the frame structure. So in other words, to have varying uplink or downlink capacity, which might also be varied locally based on case-by-case analysis of the customer requirement. Next slide, please. So just to finalize my presentation, in summary, we found that 26 gigahertz is developing rapidly. The ecosystem is expected to develop further as further deployments take place. Multiple networks are now being deployed, and I'm sure Qualcomm will describe this in their presentation. Further deployment will be incentivized by increased licensing. As I mentioned at the start of the presentation, 26 gigahertz licensing has been slower in Europe than some of the other 5G bands, but is now accelerating, and also not just in Europe where this spectrum is being made available, but other markets also. So that's the end of my presentation. Igor, back to you. Thank you very much for your time.
Thank you, Jeanette. Thank you. We will have question and answer session at the end of our sequence. So if we will have questions to you, of course, we will address it to you. So now it is my pleasure to give the floor to Tony Lavender. Tony is a partner at Plum Consulting. He is an expert on spectrum management issues and has contributed to many studies involving innovation and the economical benefits arising from the change of use and sharing of spectrum. Recent experience includes for several clients in Europe, providing advice on allocation, authorization, and potential barriers to deploying of 26 GHz spectrum, and expert input to projects for the major Asian client on the development and deployment of major private 5G network. Tony is a chartered engineer and a member of the UK Institute of Engineering and Technology. So Tony, the floor is yours, and please go ahead.
Thank you very much, Igor. And if we could have the first slide, please. This is the outcome of a study that Plum did for Nokia and Qualcomm. And similar to Jeanette's study, it's looking at a number of issues around millimeter wave 26 gigahertz in Europe. And we really focused on three things in our work: use cases, the ecosystem, and access to spectrum. Next slide, please. So, as I'm sure many people in the audience know, 5G has low band, mid band, and high band defined spectrum. We're really talking about high band here. It provides hotspot high capacity solutions, is a very good option for providing fixed wireless access in the right building sort of environments. It can potentially be used in a range of enterprise and industry vertical situations. As Jeanette's already mentioned, there's some flexibility that gives improved uplink capability, and it's a good way of optimizing costs of deployment for where you need a lot of RF bandwidth capability. In the European Union, Article 54 of the Electronic Communications Code made provisions for 1 gigahertz to 26 gigahertz spectrum by the end of 2020. We're on the road to that, as you'll see a bit later. And there's also been a number of other things that have happened at the regulatory and policy level, including the connectivity toolbox, which is setting out things that administrations can do in terms of the provision of very high capacity networks, including for 26 gigahertz. So next slide, please. So just to give you an idea of where things are generally with millimeter wave deployment, this data comes from the GSA, and it was May 2021. So you had 132 operators in 22 countries that have been assigned spectrum for 5G networks in millimeter wave. There's 28 operators in 16 countries already known to be doing this. 19 other countries had announced formal dates for plans for assigning frequencies above 24 gigahertz between now and the end of next year. And there were 112 announced devices supporting one or more 5G bands above 24 gigahertz. Next slide, please. So just to say a little bit on use cases, the picture on the top on the right-hand side is showing 26 gigahertz coverage provided by Verizon in Chicago. On the bottom is an example in a Nokia factory in Oulu in northern Finland, where 5G is being deployed. I think in terms of the solutions that can be supported in 26, in many instances, there is a need for the use of licensed spectrum and the quality of service assurance it provides. One of the issues we found when we did our primary research was equipment availability timelines, which I'll come on to in a minute. Also the need for clear communication of the timeline for standalone solutions for 5G. And at the time we were doing the study, we were already starting to get good feedback on the performance of fixed wireless access trials, which was very encouraging. Next slide, please. So the 26 gigahertz ecosystem, as I mentioned, there was concerns raised about this in our research. There's not a lack of ideas in terms of what the 26 gigahertz spectrum can be used for. It's really in terms of how does that then get translated into an ecosystem and getting access to the spectrum requirements. Band N258 is the band that we're talking about in Europe, 24.25 up to 27.5 gigahertz. That crosses over with 1 gigahertz of the N257 band, and there's at least 30 devices around now that are able to operate that in that top 1 gigahertz. that provides an opportunity to experiment in Europe, although not all regulators are allowing that at the moment. And there were definitely some clear examples of where N257 equipment had been used for trials, for example, for fixed wireless access in Italy. Next slide, please. So looking just generally at the ecosystem, so the chart on the left shows a breakdown of all 5G devices. As you can see, the great majority of those are phones. The chart on the right is showing the position on some of the millimeter wave bands. So the most populated band is N261, which is being used extensively in the United States. As you can see, N257, the 26 gigahertz band N258, sorry, the band we're using in Europe, currently only has about 12 devices in it, of which only 2 are phones, according to the GSA, as at the end of July. So this is the area where a lot more attention needs to be focused, but we expect this to improve significantly over the next 12 months as more spectrum is made available and network deployments increase. So next slide, please. So award of 26 gigahertz spectrum in Europe. There's already quite a good number of countries where the band or part of it is available, including Denmark, Germany, Greece, and the countries you can see on there. All EU countries have consulted on this. There are further awards planned in this year, for example, in Spain. But there does remain the need to actually speed up getting this spectrum to market. Russia, of course, is one country where the spectrum is already available. One of the things that stands out is that there isn't a single approach to the award of this spectrum. There's no one-size-fits-all solution evident at the moment. But I think another thing that's clear is that spectrum, you've got to have enough spectrum available to support MNOs and others who are wanting to offer service, perhaps to people like industry verticals, and that it's got to be on the least onerous technical and price terms. So next slide, please. So what were our recommendations to regulators? I think the first one is to make sure that they're regularly reviewing and consulting to see whether there's unmet demand for 26 gigahertz spectrum. If there aren't any incumbents, well, why not go ahead and make the spectrum available? If there are incumbents, look at what the access possibilities are, including the top 1 gigahertz, the band where you've got the least incumbency issues. Governments could look at implementing tax incentives or other incentives to encourage people to invest in the band. Promote the use of the spectrum with low barriers to entry, as has already been mentioned, and consider flexibility in licensing to allow localized use, as there certainly will be some use cases that need that. And the next slide, please. And in terms of industry, promote the N257 ecosystem. It's already available and it can be used as a quick start mechanism for the 26 gigahertz band in the top 1 gigahertz. There does need to be better visibility of ecosystem developments, and we've noticed this has been improving in the past few months since we wrote the report. Improve visibility of the availability of 26 gigahertz standalone solutions and really 16 features as well, for that matter. And the other thing is ensure that there's visibility of trials. There are a lot of trials going on, but people need to know about them and what the results are so that other investment is encouraged. And final slide, please. So in summary, what we found is that there is good progress on the road to 26 gigahertz. Half of the countries or half of the population in Europe now potentially has access to it. And if the spectrum and ecosystem issues are handled well, there shouldn't be any roadblocks to successful award of this elsewhere. Thank you very much.
Thank you, Tony. In Russian, we say "спасибо." And now we have to switch to the next speaker, Emmanuel Kolta, Emmanuel is a senior analyst at GSMA Intelligence, where Emmanuel provides research and market analysis for 5G digital transformation and radio access network infrastructure. Emmanuel also helps identify economic benefits for the mobile networks, which are related to innovations that unlock emerging business opportunities and improves operator efficiency. Prior to joining GSMA Intelligence, Emmanuel was a management consultant and held various analysis roles in telecommunication. So, Emmanuel, the floor is yours. Please go ahead.
Thank you, Igor. Thank you for the intro. So after this presentation, I would like to quickly run through from one angle, which is purely just the TCO, the total cost of ownership of 5G millimeter waves. Next slide, please. So we are GSMA Intelligence, the analyst arm of GSMA, and we produce roughly 140 reports a month and also have a very wide data set as well, which we can use in our reports and consulting work as well. Thank you. Next slide, please. So millimeter waves are not a new thing, and here you can see a report, a study which was published in 2000. So the whole ecosystem is try to expand the used spectrum in the last years, in the last decades as well. So what have changed since then? Next slide, please. I will have a few slides, so there will be a lot of new slides. And so what has changed since the last 21 years? And we can see that the demand for connectivity changed rapidly, and needless to say, how consumer habits changed in terms of data traffic per capita, or what kind of new services are we using, telecommunication. But also from the supply side, there was a lot of significant change. So there was a reason why we did not use millimeter waves 21 years ago. And the question is, what we wanted to understand a bit more in GSM Intelligence is, what is this reason why we did not have any devices, infrastructure related to millimeter waves 21 years ago, and why do we have a lot of deployment and a lot of new devices which can offer millimeter wave as well. So next slide, please. So we could see that also the supply of available spectrum changed a lot. So we monitor spectrum auctions in GSM Intelligence, and you can see that there are a significant number of countries in the bottom who are already offering millimeter waves and spectrum over the 24 gigahertz to operators. And next slide, please. And yeah, this is the area what I'm talking about. And you can also see that the number of connections are continuing to grow. So we actually forecast that by 2025, we will have almost 12 billion connections in the world. So obviously, the question is, can we use just the existing mid-band and low-band spectrum to accommodate and help these new connections? In the next slide, you can also see that it's not just the number of connections, but the amount of traffic what we expected to transfer is also increasing rapidly. And more than the 25%, more than the 45% of this data traffic in the end of 2025 will be 5G. So we basically have more connections and we can expect to transfer more data traffic. So there is a huge new demand and an increased demand for connectivity. On the other hand, we have available spectrum over 24 gigahertz. And the next slide, please. And when we started to work on this project, we basically identified a ratio which helped us to understand the demand for connectivity in 1 square kilometers. And as you can see in the bottom, in the horizontal scale, as 5G penetration grows, you can see that the data traffic demand in 1 square kilometer of area is also increasing as well. So to satisfy this new demand from the operators, you would need to add more spectrum. Next slide, please. And on the vendor side and on the technology side, it's not just about spectrum and demand, but there was a significant amount of efforts from different vendors to improve and make millimeter wave more cost beneficial to use. It's much more cost value ratio than it was a few years ago. So it's much more economical and it's much more advanced than it was a few years ago. Next slide, please. So we basically built a TCO model, just focusing on the cost, because we could already see that there is a huge amount of momentum and a lot of new announcement and new operators. And I think the first commercial use for 5G millimeter wave was almost 3 years ago in the US. So we just wanted to focus that what happened from the cost side. And we identified different kind of elements from the demand end and also from the network density and capacity. And so we know that how much gigabyte per square kilometer is needed. And we can estimate that we use satellite images to identify network density and consumer density and identify the difference between different
Hi, Igor. We seem to have Manuel has just come back in, so let me bring him back up. Hang on a second. Manuel, we lost you, but I think you're back.
Sorry, thank you.
Okay,
That's
no
the
problem.
one. We need a technical issue in every online interaction. Sorry about it.
Millimeter wave at your office.
Actually, that's going to be one of the part of the use case. So if we build a model, identify 3 different kind of area, FW, indoor, and outdoor. And if I would have indoor, probably I wouldn't have the technical issue 30 seconds ago. So we wanted to understand, in the next slide, you can see that in these 3 different scenarios where we can use millimeter waves, we built hypothetical baseline models. So you have 6 different baseline, let's say, an EU suburban area for FWA, and obviously we have an indoor one. We have three different actually FWA in China, US, and EU, and we have 2 dense urban macro, and we have 1 indoor. And we identified the densification requirement to satisfy the demand in these areas. So based on the number of connections, the number of need for connectivity, and we built a bottom-up cost model that what kind of network equipments are potentially needed to satisfy this amount of demand. And so basically that was a comparison between the use of millimeter wave just purely relying on the midband. And so it's just wanted to highlight that it's not millimeter wave against purely sub 6 gigahertz. We expecting to use millimeter waves in these scenarios as a complementary extra layer for connectivity. So we had several interviews with vendors and mobile operators. We use satellite images mentioned to identify the densification requirements. And in the end, in the next slide, I think you can see the key results. So we had this purely 3.5 gigahertz scenario, and we compared this one with Europe and China's dense urban deployments in a 3 years time frame. So the number, we can interpret this number that in China, for example, if the connected users are 5%, or at the moment, deploying and the whole cost of running a millimeter wave and 3.5 network is actually 13% less than just purely relying on the 3.5 gigahertz. In the next slide, you can see the results from the FWA scenarios. Here you can see that in some scenario, it's more expensive to run a 3.5 gigahertz and a millimeter wave network. But as the data consumption grew, you can see that these numbers are getting much better. It's basically mostly because millimeter waves has very, very good cost per bit attributes. So it's cheaper to transfer usually 1 bit on the millimeter waves compared to 3.5. And also, as we have more and more consumers in 5G, and 5G has higher and higher penetration, 3.5 gigahertz for mobile will be more and more busy, and it becomes a scary source later on. And the next slide, I think it's just the indoor scenario. And you can see that we have also two sub-scenario here with advanced communication equipment and with standard office environment. And that was the result of our study. So I think in the next slide, I might have a link where you can download the report from our website. And in the next slide, I would just say thank you for your time. Sorry for the technical issue. If you have any question, more than happy to answer here or in private as well. So thank you for your time.
Thank you, Emmanuel. Very interesting presentation, and really brings the cost per bit topic as it is very essential. So now it is time for the final presentation from our set of presentations, and I would like to welcome Sergey Ovchinnikov, staff engineer working at Qualcomm Engineering Services. So Sergey, please, the floor is yours.
Sergey, we can't hear you. I'm not sure if you're on mute.
Let me double check.
That's
Can you
better.
hear me?
Now
Yeah,
it
we
is
can
okay, Sergey. Now we
Okay.
hear you.
Okay, hello everybody. My name is Sergey, and I will talk a little bit more about the 5G FWA using millimeter wave systems, and we will talk about simulations. So next slide, please. So this is kind of the proof of concept that we can use 5G millimeter wave FWA in not only one way, but there are several options how we can deploy this system. And first one is dense urban deployment, which is probably not the obvious one. And next slide, please. So this simulation was made in an Asian city. It was kind of big city with this simulation cluster was in the city center. And in total, the area was around 2 square kilometers with a total number of 66 sites. So it's kind of very dense network in kind of very dense environment. So we've done simulations for sub-6 and for millimeter wave as well. So next slide, please. So the results show that if we use outdoor CPE placement, which is of course the main case for most of the FWA deployments, we can cover 100% of the area with the achievable data rates, like starting from 300 megabits per second in downlink and 50 megabits per second in uplink. So in case, of course, we will try to place the CPEs indoor, the result will be not that great, because we know that the main problem which we have for millimeter wave spectrum is to penetrate inside the building. So mainly FWA shows that outdoor placement of the CPE will allow actually to provide still great data rates. You can see that actually at a distance of 200 meters, we will see throughputs around 1 gigabit per second or more. And this is on the 400 megahertz bandwidth of millimeter wave. Next slide, please. So the other option, in case we don't have that kind of dense network in our dense urban environment, we can use millimeter wave as a kind of the fiber into the air. So we can place the CPEs on top of the buildings, and then we can provide internet inside the building with the cables. So next slide, please. In that case, we have done the simulation for the Latin American city. It's kind of the normal city with high buildings, around 8 to 9 floors. Some of them are, of course, lower, some of them are higher. It's not very universe. So again, we have the 2 square kilometers area, and we can provide coverage with this way, like to 85% of the area here. So in total, we have 2,500 buildings, and we have only 19 sites in that area. Next slide, please. So our simulations show that we can actually provide the throughputs of up to 1.95 gigabits per second. It's kind of for the 95% of the buildings. And in that case, we can provide internet to more than 15,000 families with an average of around 159 megabits per second per each family. So it's not per building, but like each family in the building may have the access to the high-speed internet. Next slide, please. And finally, what we also wanted to show, that we can bring the millimeter wave not only into the dense environment with a very dense network, but also it can be brought, of course, to the rural environment. And we have some challenges there as well, but I will show the results with the simulation, and we can see how they can be overcome. So next slide, please. So in that scenario, it was a European area near Hamburg. So this is like a rural morphology. So very small buildings, like the majority of them, it's 2 floors. And we have a lot of houses in this area. Of course, the total area is 12 square kilometers. And we have around 12,000 houses there. Of course, we will not be able to cover all of them with one site, but we can see what the simulation outcome is here. So next slide, please. So these are the some outputs of the coverage predictions for downlink and uplink. And you can see that with 100 megabit per second, we can cover up to 2,000 buildings in that area with only one site. And 75% of that houses actually will have the access to the internet of 1 gigabit plus. And we still can provide some reasonable throughput in uplink in the same area. So that's kind of the proof of concept. And why cannot we actually cover all of the area with this one-site solution is mainly to the fact that the average height of the building is around 7.5 meters, and we place CPE on the top of the building, on the roof typically. But the average height of the vegetation, which occupies around 20% of the territory of this area, is actually 9 meters. So the average tree is actually higher than the average CPE height, and that blocks the signal, so we cannot actually provide the coverage to some of the houses in that scenario. In case we will be able to bring the CPE to the height which is more than the surrounding trees, so it be in a more line of sight scenario compared to the other one, we will actually be able to provide the coverage at much higher distances. Next slide, please. And as an example of this, this is not the only one, but again, this was publicly released with Ericsson and US Cellular. Actually, we have achieved the distances around 7 kilometers in line of sight conditions. And at these distances of 7 kilometers, we actually can get 1 gigabit per second in downlink with actually peak data rates. It's possible to achieve even 2 gigabits per second. So this is obviously not the limit for the millimeter wave in case we can provide line of sight conditions. In non-line of sight conditions, the farthest which we could get into it was around 1.75 kilometers, and still in downlink we provide some great throughputs. So this is one of the let's say the best options for millimeter wave, because we still can provide a huge throughput even at the very large distances in case we can provide the signal to the CPE. That's all from my side, and we can go to the Q&A.
Thank you, Sergey. Indeed, let's have a Q&A session. So I see all speakers are on the stage now. So we have received one question from the YouTube, from the auditorium. So will millimeter wave always be a technology that mainly support mid-band based 5G systems? Or do you think that technology will improve in the future to overcome some of the limits that are seen now, limits in the distance signals, can travel, susceptibility to physical obstacles, obstructions, and so on, so difficulties with the obstruction. So I assume, Sergey, you can start. Maybe colleagues will add. So, Sergey, what do you think?
Yeah, so there is no problem, and I would say there is no limit to the signal traveling in the distance, because it will travel as all of the other frequencies do. And with the better antenna systems, we of course can transmit the signal to longer distances. So that's not the case. But physical obstruction, we will never be able to overcome, because we kind of cannot break the laws of physics. It's not the standard problem.
Yeah, indeed. So anyway, you showed very good examples with 7 kilometers line of sight and 1.5 kilometer non-line of sight. But of course, we cannot overcome the physical obstacles. Colleagues, maybe someone else from the experts can add.
No, I think that there's very little to add to what Sergey has already said. I think the other issue, of course, is with 26 gigahertz getting through into buildings will always remain an issue as well. So one has to look at an indoor and an outdoor architecture for 26 gigahertz networks. Right.
Thank you, Tony. One addition from my side, we as a company, Qualcomm, we work on the standalone solution for millimeter wave, and it will be commercial soon. So let's wait a little bit, and we will have it. So I also have one question to Tony. Tony, you mentioned tests and trials. What sort of roadmap is required for this? Maybe you can give more, let's say, details on this.
Okay, very briefly, many people have ideas for tests and trials to demonstrate use cases. What often happens with tests and trials is they successfully demonstrate the use cases with a consortium of players, but then there's no commercial road to market for that. And the reasons for that often are they come to the end of the test and trials, perhaps using spectrum which is temporarily licensed for test purposes, but then they don't have access to the spectrum on a longer term basis. So that's one barrier. The other barrier we often see, of course, is the ability to take the test and trial, which has been put together on a small basis, and scale that up into something which can be used more widely, which often requires bigger players, including mobile network operators and others, to come into those trial activities to turn them commercial. So those are two issues that we see.
Right. Thank you, Tony. So we've got one extra question, and it will be the last one because of the time limitation. So when will commercial terminals support millimeter wave aggregation with lower frequency bands? Maybe Sergey can. Or you, Tony, please.
Yeah, I think I think theoretically the answer is now.
Exactly.
I think it's really just a case of when it gets implemented into the various devices, and which I expect will come within the next couple of years. But all of there are many aggregation options already set out.
Exactly. Sergey, do you want to add something?
No.
No. Okay. Okay. So I believe we are at the end of our showcase, and I thank you very much, presenters. Thank you for your time, and thank you for your valuable information and presentations. Really appreciate your support and cooperation with Qualcomm, and I thank you, the participants of the forum, of the conference, CIS Spectrum Forum, and see you soon.
Thank you.
Thank you all.